Today we are going to look at a library called TorchAudio. So this is a specific part of Torch, and particularly for audio related model building, and we can really see it in here, a lot of functionality. So if I give you a short introduction on TorchAudio, it would be TorchAudio is a package in the Python library that provides a range of audio processing tools for deep learning tasks such as speech recognition, music classification, audio synthesis, and it's actually a lot of other techniques as well. So it includes modules for loading, transforming, saving audio data, as well as functions for computing audio features such as spectrograms and mel frequency and things like that. So TorchAudio also supports a variety of audio file formats, provided tools for audio signal processing such as filtering, resampling, audio augmentation. With TorchAudio, researchers and developers can easily process audio and integrate it to their deep learning workflow. So that was the quick intro of TorchAudio, but what I'm saying is, as we have seen in the Torch Vision tutorial, in the Torch Vision we really had a lot of transformations that we can do to an image. So here equivalently you're going to see a lot of the transformations that we can do to an audio file, and as well as different model parameters. So you can see in here TorchAudio. If I click on TorchAudio, yes, so this is just a glimpse of TorchAudio API, and this website itself is like so much descriptive, and you can come in here if you are looking at, or if you are going to do a audio based model, or let's just say a speech recognition model like we are going to do next in the tutorial. You can come in here and have a detailed look at what are the services and what are the different APIs TorchAudio is providing. So but now we'll look at just transformers and models and dataset. So since transformers are the #1 used things in TorchAudio and Torch Vision, or any of that sort of like sub libraries that Torch has, so TorchAudio has a lot of transformations that can be done on audio file, like I defined earlier, like spectrograms and things like that. So there's so here there's like resampling, fade, and volume. A lot of the features are here, can be extracted from the audio, and audio augmentation and things like that can be performed. And here we have a data set. So we will be pulling a data set from here called LibreSpeech. So as you can see it in here, yeah, this is the data set that we are going to use, which is nothing but in which is extracted from audiobooks, and we got the labels, I mean the transcriptions as the labels as well. So here we can see a lot of the tons of audio data sets are also given in here, so you can go ahead and use some of them to look at the transforms at. So also you can see models, different model weights should be really useful for you can see like a deep speech model and things like that. So we will be doing something similar to a deep speech model, deep speech 2 model from scratch. So this is just the overview of TorchAudio library, and you can just think like equivalent to Torch Vision, and when it comes to audio the things are different. So the transformations has to be different because of its file format and different data. So that's it generally, but there's a lot of tons of different things in here which you can explore yourself, and you know, when you're going to do a TorchAudio related project, you can get your hands dry with all of the transformations, and maybe you can use a pre-trained model from here, maybe you can load dataset from here, maybe you can augment using transformers, maybe you can use like functionals, which are like functional variants of different classes already implemented in transforms and other. Okay, so that's it. So with that in mind, we are going to use a couple of things from here which will be some things belonging to transformers, and also we'll take some data sets. So we'll not be using a pre-trained model, we'll be building a model from scratch on our own, something like the deep speech 2 model. Okay, so that's it, and let's get into the project. Welcome back, and today we are going to look at a speech recognition model. So first things first, we are going to import the dependencies. As usual, we'll do TorchAudio, so torch.optim import numpy, which we are going to use in some point, and from gqdm dot I need to import iter tools. I may use it, and from torch dot nn dot utils dot rnn. No, this word is not required, and that's it. So with this, we'll start our project. Here I need to make a class config, and this time config is going to have a lot of parameters saved in it. Utils dot functional nn dot function, torch dot nn dot functional. So here we'll write class config, but for now we'll leave it blank, and as we progress through the project, we'll start writing and saving all of the different parameters that we want. So the second thing that I want to do is get the data. So okay, this time we are importing the data from TorchAudio. So I will explain about the data in a bit. So TorchAudio dot datasets dot library speech, and URL equals to clean. Download equals to true. Val data equals to TorchAudio dataset dot library speech URL test clean. We're going to use test clean, and both of them. So this has to be downloaded. So the data here is the subset of something called a library speech data, which is a corpus of read English speech data derived from audiobooks. So comprising of 100 hours of transcribed audio data, and it's really easy to download as well. So what you're going to get from this data is nothing but a bunch of information about different audio files. So you'll have the tensor equivalent of a wave file. So once you start looking at the inside of the data, what you're going to see is different audio files, and also the transcribed labels of the audio, with a bunch of other stuff as well. But we are going to take explicitly the audio file as well as its label. Now, one thing we have to take care of in here is all of the different audio files are going to be in different lengths. In order for us to be able to perform training in a batch, our samples has to be of same size every time we run through a batch. So we will need to do some sort of transformation first, and also some kind of padding for every audio file to be of the same length. So what we are going to perform in here is nothing but we'll convert the audio files into tensors, and we'll have some sense of some random dimension, and the length spectrum of the audio is going to be of different lengths, because every audio is going to be of different lengths. So we cannot deal with that. So we will need to pad them maybe, and we'll need to come up with the pad size, or we'll need to come up with a shape that everything else can be padded to. Train data dot, okay, so this is how the data looks like. So the zeroth element in what we get from the train data is nothing but the tensor equivalent of a wave file, and then we have the label in here with a bunch of other stuff. So what we are going to take is this tensor and also this label. So this tensor is going to be of an arbitrary dimension every time, because of the length of a sentence, or a spoken sentence is going to be really different depending on the sentence. So we will do some sort of padding to make it of the same size, so that we can train in batches. So that's what we are going to do. But apart from that, before we batch or pad or anything, what we are going to give is some different transformations. So for the training data, we will be giving 3 different transformations, which are Mel spectrogram, frequency masking, and time masking. So the reason why we would do this is because people have been using different techniques, but the spectrogram augmentation is found to be really simple and effective. In here, we'll be cutting different random blocks of consecutive time frequency dimension. So the reason why we do these transformations are because it is effective. So we will be converting our tensor into a spectrogram, and later this spectrogram will be cut at random places in its time and frequency dimensions. So in this transformations, what we really do is we transform our tensor into spectrograms, and later in the time and frequency dimensions of the spectrogram, we would randomly cut different parts, different consecutive parts, and this is going to actually enable some sort of generalization in our training. So let's look at how we can give this transformation. So of course the transformations are coming from TorchAudio. So I will write train transforms equals to nn dot sequential of TorchAudio dot transforms dot and we have to give a sample rate, and the sample rate here is going to be 16,000. N-wells corresponds to the number of feature dimensions, the dimensionality of the feature space. So what we are going to get after this transformation is something like a batch, comma feature, comma a timestamp dimension. We're going to essentially break our audio file into different audio file into its timestamps, and also we will have a feature dimension. So this feature dimension is something that we can define through nmels, and that is going to be a constant every time, but the timestamp dimension is going to be different for every different audio. So we'll need to pad or do something like that, so that everything will be equally a tensor, everything be a tensor of equal size. So in the configuration I'm going to write, and here also in nmels I'll give config dot input features. And after this we'll need to give TorchAudio dot transforms dot frequency masking, and I'm going to give mask param, say. Once you look at the TorchAudio documentation, all of these parameters will be clear, and we'll do that. I'll also define val transforms, and I don't want anything except this mel spectrogram, and then dot sequential of TorchAudio audio dot start mel. And in our sequential mel spectrogram. So okay, once every tensor is passed through this sort of transformation, that's the data that we are going to use essentially. So once it is passed through, as I mentioned, we are going to get a tensor of pad size and feature size, and a timestamp dimension. So that time dimension is going to be different, and we need to pad them. But before that, we need to know what is the maximum time dimension, so that we can pad every other sequence into that dimension with some zero padding. So for that, I'm going to go through all of the data and figure out which one is the highest, the lengthiest audio. So all data, and along with we'll also figure out some other features. So all dot chain. So what we can do is itertools dot chain. What it does is it combines two iterators or multiple iterators. You can combine them. So here the train data and validation data, I'm combining them, and I need to find a value that both of these data points can be padded to, so that everything would be, and in a batch size it can perform. So I'll say tensor max length equals to an arbitrary value. The reason why I'm giving -1 is because every tensor is going to have a positive shape. Tensor max length, and label max length equals to -1 as well. And for instance in all data, all data. What we're going to do is data len equals to train transform of instance of 0 dot shape -1. Train transforms to instance of 0. Yeah. So what I'm trying to extract here is I am taking an instance, and instance would be of this sort, and I'm taking the tensor from them, and I'm passing that into this transformation, and after that I'm taking the dimensionality, the time dimensionality of the transformation. So ultimately what I'm going to find is the maximum overall the data of this dimension. And the same for label as well. Label is just a text, just a string, so that also we are going to look at it the same way. So the highest the longest text would be the dimension of the longest text is what we are going to pad every other text into. So labeling equals to len of instance of 2, and if data len equals to tensor max length, if data length is greater than tensor max length, if this condition satisfies, then we would say tensor max length equals to the other one, data len. So exactly the same for if label length, I think this is label length greater than label max length. Label max length equals to I'm writing this because I need you to actually understand this thing. Otherwise I wouldn't actually have to write a lot of very descriptive code for this one. Okay, so now that we've done that, we can look at the tensor max length and tensor max length comma label max length. When you TorchAudio transform as an attribute melt spectra, okay, that's right, because okay, torch vision is not defined, so TorchAudio, I said TorchAudio. So autocorrect is the problem now. Toggle line numbers, iter tools. Okay, we got it. So this is the maximum length of the audio, and this is the maximum length of the label. So we can take these two numbers and pad every other data and label into this numbers correspondingly. So in this problem, our labels are text, and this text are it's just a string. This text is so our labels are just a string, just a long string. So what we need to do is encode them in some way. So encoding them means we need to convert them into some integer representation. So I'm going to do it by hand, and we are going to take like a couple of the there are different characters that are actually in the data itself. So there are like A to Z alphabets, and then there's a period and a space. So these are the only characters that we have in the data. So these are the only things that we need to encode for. And once we encode it, we need to come up with a way to change the text into completely a list or a tensor. And once we get a tensor output, we need to make a function to convert it back to alphabets as well, or words as well. So let's do that. So alphas, I would write, as I said, these are the characters that they have. This is one of them, and a space bar. Then we have A, B, C, to. So you can fast forward this thing, or I will fast forward this thing. So we have our alphas now, and nums equals to range 28, because there are 28 characters in here. Alphas to num, or alpha to num, alpha to num, and there's a dictionary. I'm going to make an alpha to number dictionary, which should be nothing but a dictionary of alphas. Alphas of I, nums of I, for I in range len of alphas. And now num to alpha dictionary, and this has to be the opposite of that. So v comma v and k for k comma v in alpha to num dict dot items. So this is going to make a dictionary that is the opposite of alphas to num. Okay, fine. So now I'll define a function num to alpha, for num to alpha, which takes a number, and this is going to be a tensor, and we'll return something called num to alpha of num to alpha dict, and from this dictionary we'll take the number dot item. We'll take the key, and similarly we can also define alpha, or alpha to num of alpha. This is going to be an alphabet or a string, and return alpha to num, and we'll take this key, the value, and we'll pass in the key alpha. And one important thing is we have given it in lowercase, so we could be having our data in upper and lowercase, so we need to be in the same page in here, so we need to convert that into lower, everything into lower, and we will search in here. That's it. So that functions are done. So we'll come back to that function later. We are going to at least use one of these functions. So one of this function, to talk about this function is one of them is going to be useful in encoding, the other one is going to be useful in decoding. So if you want to figure out different matrices and everything, once you have an output and you're converting your output into predictions, and then you want to convert back to sensible text, so at that point you're going to use num to alpha. But when you have alphabets coming, like the labels of this data, and you want to convert that into numbers for training, then you're going to use this one. Okay, so now the most important thing, class data loader. Data loader. I think I'll zoom it a little bit so that you can see it better. Okay, so data loader, class data loader, and it's going to take define init self comma data comma transforms. So this is going to take data and transforms, so I can take either the validation data or the training data that we defined in here, and we'll apply this transformation that we have already try to do it in here for finding the best the maximum length. But we'll be doing that for real now here, and we will try to output the data in some certain format. So define self dot data equals to data and self dot transforms equals to transforms, and define get item self comma index so a single audio file comma transcript, and its transcript equals to self dot data or self dot I'll transform the data as well, transform. So as I have already shown you, the 0th index is the tensor, and the index number 2 is the label or the transcript. Self dot data transform self dot data of idx of 0 comma self dot data of idx of 2. Now again, single audio, we need to extract a couple of things here. So single audio equals to, so now is the thing, so we have about 2 different tensor max length and label max length. So we'll pad training data train x into tensor max length and labels into label max length. So for this we'll use TorchAudio and torch.nn.functional, which we have already imported. So f.pad single audio, and for padding you have to really look at the padding documentation on Torch, so that this is going to be easy for you to understand. So what I'm going to do is nothing but just don't worry about this one. What I'm going to do is pad this sequence in its final dimension, which is the dimension that we are going to pad, because the final dimension that we have is the time dimension, and that dimension is exactly what we are going to pad into the maximum length. Zero tensor max length minus single audio dot shape 2 and we need to say okay. Okay, so we had a little problem here. Okay, so mode equals to constant and value equals to 0. So now single label equals to f dot pad pad it later then. So here torch dot, we can do torch dot tensor. First of all, we need to convert that into tensor. So these are text, and we need to convert that into numbers, and then those numbers are going to be in a list. So we are going to return, we are going to use this alpha to num, and we'll return a list of numbers for a list of alphabets, which we will take from the labels. So we have the labels, which are text, and we'll convert that into a list of alphabets, and then that alphabets will be converted to a list of integers, and that integer will be converted back to a tensor of integers, and then that will be padded. So tensor of list of map of alpha to num, and alpha to num, and transcript. Transcript is what we have written here. Transcript, and we can specify data type is equal to torch dot long, which is in 64. And now we need to return, as usual, I'll return a dictionary. So in this dictionary we are going to have different things. First is data, and data is going to be single audio dot transpose -1, -2. The reason why I'm doing this is I need to have the feature to be the final dimension for me to be able to give that into any of the model that I'm going to create. So the model that I'm going to create would expect a feature dimension of 128 as I specified, so as I given in the config file as well. So that's what I want in the final dimension. So right now what I have in the final dimension is the temporal feature, which is something that I've padded. So I have moved that into the previous dimension, and the final dimension will be the feature dimension, which is a fixed dimension. Okay, and now label, and this label will be torch dot nn. Oh, I don't have to do this, but I can do functional f dot pad. So single label, and the single label will be taken, and we'll pad it 0, label max length minus single label dot shape -1, and again we have mode equals to constant, and value equals to 0. Now we'll have to have data length. So the reason why I'm doing this is because the loss function that we are going to define is going to take a couple of more things than the conventional train x and train y, or x and y in more general terms. So this is going to take the length of the original length of the input, and the original length of the label as well, because when we are giving in batches, we are padding it and padding it to the maximum length. But even if we are padding it to the maximum length, the loss function would ask you what is the original length of the data and original length of the label, so that the padded elements can be removed, and it can be the mathematics can be done conveniently. So that's the reason why I'm taking the original length information as an output as well. So this original length would take what is the original length of the single audio and transcript. So at this point, what we have is something of a fixed dimension for every audio that is coming in and every label that is coming in, which is going to be of a shape batch size and this size, and 128 for training data and batch size, and 576 for labels. But we need to preserve the original information, and that will be returned as well. So here torch dot tensor of single audio dot shape 2. This is a single audio. Okay, single audio dot shape 2 comma d type equals to torch dot long again. And the same way I'll also write label label length, and label length will be torch dot tensor of the same way len of transcript, and this also is going to be of the d type torch dot long. Okay, so I'll need to define limit underscore length and self, and this is going to return the length of self dot data and return. That's it, our data loader is finally done, and we can initialize train loader. Val loader. Train loader equals to data loader, which we have imported, and we also looked at this class earlier a couple of times. Our data loader function, and inside train data comma transforms train data comma transforms equals to train transforms. Yeah, and we can have batch size boom and shuffle equals to true. So this batch size is going to be as config dot train batch size, and I'm gonna come up in here. In this project I'm going to come up into config a lot of the times, so I'll write something like this is more of an optimization related so that once I'm like compartmentalize it, it's going to be easy to navigate. So train, let's just say train batch size equals to 8, and val batch size equals to 8 again, and let's just say epochs equals to, so it is so early to actually define the epochs, but I'll just give it a dummy number, and that's it. And we write a lot of other things in here configuration related, and val batch size also defined. Okay, so let's go back in here and copy this thing and edit it, and it's going to be val data, and transforms equals to val transforms, and config dot val batch size, shuffle equals to true. Okay, we'll run it and see if everything is working. I think we have run this one also. Okay, either way, so iter of train loader equals to TL for train loader. This is for testing. I'm just testing it. So next of TL if everything is working perfect. So no, nothing. No, it's not working perfect. So transform. So there's a typo. Transforms. So we're in line number 7 in get item. Line number 7, and I've written transforms. Is that okay? No. Another typo. Function object is not subscriptive. It's because I made a mistake here. So this was supposed to be DICT. Finally, we got it here, and we'll look at its keys. Okay, data, label, data length, and label length. We'll also look at data dot shape. We need to see that it is got the same shape as we mentioned. So what I'm going to do is a small editing. So for the processing purposes, in the testing time, I'm going to give the batch size into our number size. Otherwise it's going to take a little long time because it's a big tensor. Okay, so this will rerun this one. So at the time of training, we are going to definitely change this one, but at this time for testing, we don't want to waste a lot of time. Okay, and again we'll run this one, and we'll run this one. So you can see here, so 120 is a feature dimension that we fixed, and this is comfortably padded into the maximum dimension, which is right in here. And also if you look at label, it should be padded to 576 labels as well. So that's 576, and label length and data length. Okay. Yeah, the shape is going to be 1, and if you want to look at the value, its length is 776 characters. Okay, finally we are done with our data loader, so a big part is over. So now we need to get into another big part, which is the model. So in this case, the model is going to be a little complicated, and after the model has been done, there isn't much we have to do in this project. It is over actually. So but the model part is going to be a little hectic, in the sense you'll have to have a good understanding of what a convolution is, and you have to have a good understanding of what bidirectional GRUs are, or at least placed RNNs are, and everything like that. Okay, so we are going to have a lot of layers in this one. So we are going to use convolutional layers, we are going to use GRU layers, and we are going to use different normalization techniques, different dropout layers, different nonlinear activations. Okay, so let's just get into this one. So I'm going to do it as systematic and structured as possible so that you get a good understanding. Also, in this model class, I'm not going to take any parameters. All the parameters is going to be defined in config. Okay, so let's start this part. So we'll define layer norm. We'll write a layer norm layer, input features, and I'm going to make a separate. This is going to be out of the model. This is more of an independent layer inside a function. So layer equals to nn dot layer norm, and inside I'll do input features, layer norm of input features. So layer dot to, we'll need to do config dot device, because at the time of training, otherwise this is going to be only in CPU, and all the other things are going to be on GPU of X. And in the config, device equals to our same CUDA if torch dot CUDA dot something is available, otherwise CPU, right? So if torch dot CUDA dot is available, else CPU. So we pass that layer into, this is nothing but a layer normalization. So this layer would normalize the layers given input and the features. So these are the x's, and these are the layer, the dimension in which the layer has to be prepared. So these two parameters will be passed in, and in multiple places that we are going to use this thing. So the next thing that I need to define is a class. I'll write this residual CNN of nn dot view, and this is going to be a bunch of convolutional layers. So we'll do initially the data in the torch. The audio data is something that we haven't seen before. So if you think of the old audio data, it's coming in 3 dimensions. So it can actually be visualized like you're looking at a picture. So once you have the way you have dealt with a picture in any of the computer vision problem, so you can think of it like that. So once we are applying the convolution, it is going to undergo the same sort of mathematical and same sort of geometrical transformations. So you can visualize it in that way, and it's going to be really exactly the same, except for the data type is different. The data is coming from the audio data, but it is actually a tensor, and once it is a tensor, it doesn't really matter what the source data is like. So a tensor of some shape, and we can apply convolution. So you just don't have to channel convolution operation into only for computer vision. So convolution operation can be applied in multiple fields, and this is one prime example of that. Define init of self, and then write in channels, comma out channels, and I need a kernel, a stride, a padding, a dropout probability. Okay, I will be descriptive. Dropout probability and input features, because we will do some layer normalization and we need input features in this class. Now we'll do self dot input features equals to input features. We are going to have a lot of typos in here, I think. Input features equals to input features, and self dot conv1 This is where things start to get interesting. nn dot convolutivity, oh, come two dimensional of in channels, out channels, kernel size, stride, and padding. In channels, out channels, out channel, and in channel, and kernel, stride, and padding. And our convolution 2 dimension is going to be, we are not going to change the channel size in here, and self dot, we'll need to define a dropout 1 and dropout 2, nn dot dropout of dropout. It's exactly the same, so you don't actually have to write dropout 1 and dropout 2. I'm just doing it to make it look like in a certain way. So now we'll define forward of self, comma, batch. So batch is coming, and here we need to give, so we'll do something like batch equals to f dot klu activation, and we'll do layer norm was defined like layer norm of batch, self dot input features. Okay, and this is the batch, and we'll do now a okay, so batch again equals to self dot drop 1. We'll do the dropout 1 of batch, and now we can do batch equals to self dot convolution, self dot convolution 1 of batch, and I will essentially, you're going to do the same thing, and there is not much difference except for I have named it 2. I didn't actually have to name it, you don't have to name it, because the probability is exactly the same, but convolution is exactly not the same. I'm only strictly talking about the dropout layers. Date GLU layer norm of batch, and batch equals to, I think I'm doing right, 2, and yeah, so here we need to get equals to residue. We need to add this residue to the final output, so batch is also going to be the residue, residue equals to batch, and we'll do return batch plus batch plus residue. So that's what our convolutional layers are. Now what we're going to do is bidirectional GRU layers. So I'm going to initialize a different class for that. Class bidirectional GRU of nn dot ju, and this is going to take all the things that are necessary for a GRU. and some dropout probability. So define init self, and later we are going to define all these functions inside of a configuration file so that I don't have to initialize every time a class with different parameters. I only have to give it inside. So essentially all the parameters are going to be global parameters rather than in a class. Self input size, hidden size, and number of layers, num layers, and what we need, dropout probability. We'll do this, and we need to say super.init, which we did not say in here, so we forgot one important part in here. So this is not going to work because so the same way and self dot bidirectional GRU equals to nn dot GRU input size equals to input size, and hidden size equals to hidden size, comma num layers equals to num layers. Okay, and batch first has to be true here because the incoming data is batch first, kind of batch comma temporal dimension comma feature dimension. So bidirectional equals to true, bidirectional equals to true, self dot drop equals to nn dot dropout. Need to give that dropout layer here, and the dropout probability. Define forward self comma batch, we will batch equals to f dot GLU layer norm, and this layer norm, okay, layer norm batch comma self dot what do we have, layer norm of batch and self dot input size. Yeah, that's our input size, I think. So here also input features, but here it's input size. Batch equals to self dot bidirectional GRU of batch, and batch equals to self dot drop batch of 0. This I'm writing batch, let's just say batch of here it's a little tweak here, so you will be clear why I'm doing this. Later else batch. So let's just not think about this one right now, so we'll come back to this one and revise this one later. So return, it's because we could be having some discrepancy of like what is the type of this batch. It could be sometimes be tuple, and if it is tuple, we just want to take like the batch inside of it, so we'll take like drop out batch of 0, otherwise we'll definitely take like batch itself. So that's it. So it's like very minute of a detail, so you can figure out a different way to way around this if you have any idea. So this is just more of like a quick fix to an error. Okay, now we'll write the speech recognition model class speech recognition model of nn.visual, and we do define init self, and it doesn't take anything, that's all, and super dot, that's all. So we're not in it. So self dot cnn equals to, okay, now we need to define all of the layers that we defined in different classes now. So this is our main model is going to be, and all of the different things that we defined like layer normals and 2 different classes for residual CNN and bidirectional GRU. So we're going to initialize them, instantiate them inside of this this class, the speech recognition model class, which is our final model class. So we're going to initialize both of these classes, and we're going to use this function. Already we have used this function inside of this class, so everything's going to be inside here in speech recognition model. So we'll also define a couple of other layers in here. So first thing that we're going to define here is an initial convolution, self dot cnn equals to nn dot convolution 2d, and in channels equals to 1, out channels equals to 2, oh sorry 32, and funnel equals to 3, and we'll do stride equals to 1, and padding up also equals to 1. Self dot linear, another linear layer that we can define, and then dot linear of so a linear layer that we are going to define is going to be set in between these 2 layers of residual CNN and bidirectional GRU. So what we are going to get from this is essentially a box like a three-dimensional output, which is going to be batch comma time dimensional comma feature dimension. But what we need to make is make that into a long linear layer, and later that linear layer be passed into the bidirectional GRU, and then we will process in that order. So we need to have a linear layer of some dimension. So for that I need to define a lot of parameters on config here. So what I'm going to do is I'll go to config and I'll define some parameters for all of the models, all of the models that we define in here. So for residual CNN params, we're going to do what we're going to do is residual CNN input channel is equals to 32, and we got output channel residual CNN output channels equals to 32 as well, and residual CNN kernel size res CNN kernel size equals to 3, and res CNN stride equals to 1, and also res CNN padding equals to 1, and let's say res CNN dropout probability equals to 0.1. Okay, also for bidirectional GRU you can define some of those. So bidirectional GRU we will write GRU bidirectional RNN input size is going to be 512, bidirectional RNN hidden size is going to be 512 again, and bidirectional RNN num layers, number of layers equals to be 1, and again RNN of dropout probability is going to be 0.1. We'll change this, or we can change this. Even if I don't show you changing this, you can always hyperparameter to using changing this. And we're going to have a final classification layer as well, but we'll come back to that. So our linear layer is something that takes the convolution, the final layer of the convolution, into an input size in the RNN. So input size in the RNN is going to be different, so that's the reason why we have given here also in once we have given layer norm, we have already taken self dot input size, so that self dot input size is going to be different from 128. So here the input size is going to be 512, and that's the reason precisely why we have given it in here separately. Otherwise we could have already given it assigned it to a global variable, but here this is not a global variable. Okay, self dot linear and n dot linear of what we are going to write. We need a linear function. So this is going to be config dot press CNN output channels star config dot input features comma config dot bidirectional RNN input size. So we are making this into a two-dimensional tensor, so that the final dimension is going to be the bidirectional config dot, what is this, config dot input features and config dot bidirectional RNN input size, so that this will be x comma y and the y is the input to our RNN and x is the rest of it, whatever we have from CNN. The rest of it will be accumulated into one of the dimension, and the rest of the final dimension that we require has to be of the feature dimension is precisely given as the feature dimension. Okay, so self dot res CNN will initialize. What we are going to have is a CNN, multiple CNN layers. So we have to find a class of CNN here, but we are not going to have just one of this layer. We are going to have multiple layers of this sort. So we need to also define how many layers we want in the config file. So we can write in a dot sequential of, and or we can pass in a list, and this list is going to take, and we need to unravel the list as well. So list of residual CNN, and we're going to say in channels equals to config dot press CNN input channels. This is going to be a little hectic because I have defined lots and lots of parameters inside here. Press CNN of okay. Why do we have a comma here? Okay. And input channels output channels equals to config dot press CNN output channels kernel equals to config dot press CNN kernel size. Yeah, and kernel is ready, and stride and padding and dropout property stride equals to exactly the same config dot, make sure your config is capital C, otherwise I'll need to do a lot of debugging. So stride is equal to config dot press CNN stride, and padding equals to config dot press CNN padding, and what do we need? Dropout property. equals to dropout probability, and finally input features config. This requires a lot of patience to write. Config dot input features. Okay, finally, and I'm going to say this in I'm going to say what I'm going to say for in range. I need to have another parameter on config, so config dot num res CNN. So this many residual CNNs will be implemented, and I'll define num res CNN. Okay, let's just say equals to 3, and num RNN equals to, let's just say 5. Input features is something that we already defined. Let me keep it in here so that it'll be easy for me to look at. And batch size and everything is defined. Input features equals to, okay, so these are the number of layers. I think we have all of the parameters that we require for now, and we'll go back to writing our final model. So now we'll write self dot RNN layers. RNN layers equals to be exactly the same method, nn dot sequential, and inside of the sequential we are going to again implement a list, and we'll unravel it, and we can say, hey, we can say stuff like bidirectional, bidirectional GRU, and all of the output that input that it takes. Input size equals to, okay, here there's a tricky thing about input size. So since this is bidirectional GRU, the input size here, what we have defined was 512, and why 512? It doesn't really matter what sort of dimension that we are going to give. We can give whatever the dimension we want. So 512 is just a dimension. That's just it is. So you can also change it around and experiment on it. But what I'm telling is, once the input size is, so if I want to make multiple bidirectional GRU layers, then it's going to be like it cannot be like always taking input size equals to 512, because it's bidirectional, because its output is going to be 512 into 2. So the next time you implement a bidirectional GRU, you need to take care of that too. So it's going to be 2 times, so you have to take care of that. Okay, GRU of input size equals to, we will now say bidirectional GRU of input size equals to config dot by RNN input size. If I equals to 0 and else we'll say this is twice config dot by rnn input size, and we have forgotten to keep comma here, so you have to keep comma. Okay, so here also comma, and hidden size equals to config dot bidirectional rnn hidden size, and num layers equals to config dot bidirectional rnn num layers, comma, dropout probability equals to config dot bidirectional rnn. Oh, no, by rnn dropout probability. I think I have defined that one as well. Oh, bidirectional and dropout probability. Okay, and that's it. So we can take it here and we can say for I in range config dot config, so config dot rnn num rnn. Okay, and we are done with that one as well. So once we get the output from that layer, so it'll be clear once we go through the forward pass. But now you just have to concentrate on what are the layers and what are the constructions of the layers and how many layers and different stuff we are adding and so on and so forth. But once I'm defining the forward pass, it'll be clear how am I going to at what point in time am I going to apply each of these layers and what are the relationship between all of this all the parameters that we have written on config file. So the final thing that we're going to write is self.classifier self.classifier equals to nn dot sequential again, and this time we're going to do nn dot linear layer. This is more of a classification head. We have already looked at the classification head in the previous problems in BERT and everything. CL input input size. This parameters has to be defined now, because once I get this thing, okay, let's just discuss this thing when we talk about the config. We talk about the forward pass. So CL input size, I'll half it, and nn dot config dot CL input size and CL dropout probability also I'll need, and also CL. Okay, so what I'm going to define now, I'll go back to the config and I'll come back to this point again. So we need to define a couple more parameters related to the classification. Okay, as I have already left a space for it here, and CL, we need to say CL input size is going to be bidirectional RNN input size star 2. So we have the bidirectional RNN input size equals to 512. So the output of GR is going to be twice this quantity, and that's what our input has to look like, because the input to this classification head is more of like linear layers and dropout probabilities, so it has nothing to do with convolution or anything. So ultimately what we need to do is we need to what we are going to receive is a flattened 1024 weights. So these weights has to be encoded to a dimension of the same, and that dimension is going to, we're going to reduce that dimension further and further to get the predictions for the labels. So the labels are going to be also I'll discuss it right now, so that you have the picture, the entire picture as you watch the video. So what I'm going to do is I'm going to further and further, so in the classification layer, I'm going to further and further decrease the number of outputs, the logits that we want. So finally I need to get 29 logits. So all of these 29 logits will be something that corresponds to all of the alphabets I have written down. And let's just say that I need to predict one alphabet at a time from every timestamp dimension that we have. So let's just say now we have, for every data coming in, we have some sort of a size of batch size, comma 2707 comma 128, which is the feature dimension. So this one is the temporal dimension. So every temporal dimension, so 2797 temporal dimensions, I need the logits for 29 outputs. So we are going to have 2797 cross 29 of an output, and also batch size would be there. So for every temporal dimension I want the best probability, so I want 29 outputs. So then that 29 outputs will be passed in through a softmax and then an argmax, and we'll find out which is the best predictions of each temporal dimension. So for that we need to get the output as 29. So why 29, you may ask? It was like 28 when I defined here. It was like 28 alphabets and characters included. It was 28. So 29 extra one comes in when we want to use the CTC loss that we are going to use. So I'll talk about that when I define the CTC loss. So we are in here, and nn dot I'll give a Gelu, and nn dot dropout of config dot cl. We have dropout. We did not define a dropout probability. Like, I think we have not defined everything. Oh, okay, we only defined one of them. Okay. So we're going to define CL dropout probability. CL dropout probability is equal to 0.1, and CL 2.1. and cl num class num classes equals to cl, and cl num classes equals to 29. We'll come back, cl okay, fine. We have a typo again. Dropout probability, and after that nn dot linear of config dot cl input size by 2 and config dot cl num classes. So that's it. So now we'll write the forward pass, define forward of self comma batch, and in here I need to define the time dimension, because okay, you can watch this. Batch dot shape 2 is going to be our time dimension. Batch size equals to batch dot shape 0, and output equals to self dot cnn of batch, out equals to self dot residual cnn of out. So we have done the cnn layer and then the residual cnn, and now we'll do out equals to out dot view, and that's a batch size. I need to batch size comma time dimension comma config dot res cnn output, config dot res cnn output channels star config dot input channels, input features, input features. Out is going to be equals to self dot linear of out, now we'll do out equals to self dot RNN layers of out, and again output equals to self dot we got a classifier of out, and we can return out. Okay, so what we are doing here is, at first we will have only one batch, only one input channel for every batch. So in the CNN, what we are doing is we are changing the number of channels that we have. So we are changing the number of channels to 32 channels. So once we have that many channels, our dimension is essentially going to be different. So after from the output of the CNN layers, the dimension of the incoming batch is going to be different. So once we have that sort of a different output, what we're going to have is to be compatible with that output, we need to proceed designing our RNN layers to be compatible with that sort of a dimensionality. So that's the reason why we have changed our data and the input into some dimension, comma, the input dimension that we decide. So we took every dimension and we made it as its first dimension, and we don't really care about that dimension. But the only dimension that we care about is the input dimension for the RNN that we decide. And once we have done that, we need to view it in a certain method. So the certain view is what gives its freedom to be coded into a linear layer, because we need to be ultimately looking like batch size and time dimension and a feature dimension. The feature dimension is going to be a product of the channels coming in and also the input features, and then we directly encode that into a linear layer, and then the the RNNs will give that into the RNN so that the input shape and everything is the same, and then we give that into the classifier. Invalid syntax of 46. Yeah, I equals to if I sorry, equals to 0. Okay, that's perfect. Our model is done. So now we'll define our model. Model equals to speech recognition model, and model equals to model dot to config dot device, and we need an optimizer, which is optim dot rmw, and I will write model dot parameters comma lr equals to config dot lr, and in configuration we need a learning rate. Lr equals to 1a minus 5, let's say. And we also are going to implement a scheduler. Scheduler equals to optim dot lr scheduler dot one cycle. We're going to use this one. So I'm going to link you a couple of things that you have to be reading to understand why am I using certain things here. So I'll also give you a blog on what exactly is CTC loss doing. So that is going to be really helpful once you read that thing. That's exactly what I'm going to implement here. Optimizer and max lr equals to config dot So this is going to take this scheduler is going to take a maximum LR, and it's going to keep on increasing. So it is going to like keep on increasing to the maximum LR running rate, and then it's going to decrease it to the minimum value. Max LR equals to config.lr, and step per epoch equals to int len of train loader. And we get this thing. Epochs also has to be equals to config dot epochs, and we can do annual strategy. Linear. We need to define a criterion equals to CTC loss, and then dot CTC loss. So what CTC does is it is going to give you the logits for each of the timestamp. It has the, so sometimes when we have audio timestamps, we might not be able to understand what is the character or what is the alphabet that should be produced at that particular point in time. So there could be different scenarios. So there could be in different consecutive time steps, you could be having the same alphabet, or some particular time step the model could not be finding, model might not be able to find an alphabet. So at that time the CTC loss has the power to actually give an unknown token, sort of like we can say blank equals to CTC loss of blank equals to 28. So once I say blank equals to 28 and CTC doesn't understand what is the alphabet related to a particular timestamp in the data, then it's going to give it the token 28, and 28 it doesn't really have anything in any dictionary. So whenever we get a 28 as an output, we'll just leave that. We would not take that timestamp as to decode it. So all the other things can be decoded, but 28 is blank, and it cannot be decoded. It is unknown and not understood, sort of. And I need to change this to my device. Okay. To write a class train, I'm going to write it as a class and define init self and comma optimizer comma scheduler comma model comma criterion, and self dot optimizer equals to optimizer, and self dot scheduler equals to scheduler, and self dot model equals to model, and self dot criterion equals to criterion. And we're going to write define just like we have done it in the past. So self comma train loader, this arbitrary self comma train loader. Okay, and so I need to get the losses. So what I'm going to do is define an an empty list for documenting losses. For idx comma batch in enumerate train loader, and if you want, you can give, if you want to see in training how it looks like, then you can give tqdm and wrap it around this one, and you can also give a description equals to training and total equals to, this is because we need to for the first time when we are running, we need to be making really sure that everything is going the right way, and we need to, I'd like to personally see if it's running in its inner levels or not. And train x equals to batch of data dot do config dot device. Train y equals to batch of label dot do config dot device. Out equals to self dot model. We need to do a couple more things. Self dot train y, so train x length, we don't actually need it. Train x length equals to batch of data length and train y length equals to batch of label len again. Okay, so output equals to self dot model of train x, and output again equals to f dot log softmax of output comma dimension equals to -1. And for output to be given into the loss function, we need to transpose it, so it expects it in a certain way. So it expects that the time dimension to be coming at first in the 0th dimension, and the batch to be coming in the 2nd dimension, and the features to be the 3rd dimension. So we need to transpose it accordingly. So out dot transpose 0, 1, and we would say loss equals to self dot criterion so self dot criterion of output or out, and our train y, and also our train x length, train x length comma train y length and a comma. Okay, so losses dot append loss dot item and loss dot backward and self dot optimizer dot 0 grad. And self dot optimizer dot step. Now self dot scheduler dot step, and that's it. We had 3 steps, and we'll return np dot mean of our losses. Okay, that's about we defined fit. So now we can define predict. predict also of self comma val loader, and losses here also equals to this kind, and we'll wrap it with torch dot no grad for idx comma batch in enumerate val loader. What do you do here? Okay, so here also I'm going to give a TQDM for you to see it and for me to see it as well. DSC description equals to it's validating. I think it's a random description that would describe it. That would be fine. Total equals to len of I need to make sure that okay, len of val loader, and valx equals to batch of data. So what you need to do is batch of data and batch of this thing. Oh, sorry. Oh, we'll do batch of data, batch of this one. Exactly, this is what you need to do here. Okay. So valx comma val y equals to val x length, val x length equals to val y length equals to. Okay, so now we need to take output equals to self dot model of valx. Now output equals to so f dot log softmax of output comma dimension equals to -2 -1, and we'll also transpose output equals to out dot transpose 0,1, and we'll do loss equals to self dot criterion of output comma val y comma val x length comma val y length, and losses dot append loss dot item, and return np dot mean of losses. Okay, and now we'll have to define here train equals to train of optimizer comma scheduler comma model comma criterion. Okay, train losses train losses equals to this val losses equals to an empty array, and we call it for epoch in. We can also give a TQDM of epochs, that's config dot epochs in range range of config epochs, and total equals to, okay, you don't have to give it, that's fine. And train loss equals to train dot fit train. This is our original train loader, not a placeholder. Val loss equals to train dot predict val loader, and so our train losses dot append train loss, as well as val losses dot append val loss, and that's it. And we are actually, this is our training loop, so we are actually done writing a training loop. So all we can do is plot it. So you can import matplotlib dot splt and plt dot plot of range len of let's say val losses, range len of val losses comma val losses okay, and I can write changes into train, and here also train, and plt dot legend validation and training, and that's it, and we are done. So now we'll try to run this thing. Okay, so now that I have turned on the GPU, and this should be running now, and it should be running without a problem now. And I have done a couple of decoding, a little bit typos and things like that, so it should not be a problem. So we'll try running it right now. So it's running now. It is running perfectly now. So after that, this should be plotted. So I'm running it for like 2 epochs because I just wanted to look at it. So you can run it from multiple epochs and check the loss function and any other metric that you have. Okay, so we will wind it up here.